All right, today we are diving into the science behind a perfect medical image. It's pretty incredible that doctors can see right inside our bodies, right? It's one of the biggest wins for modern medicine. But getting that perfect, life-saving picture, yeah, that's way more complicated than you might think.
What really is the difference? It's a question that goes so much deeper than just, is the picture clear? The answer is this really delicate dance between physics, engineering, and what the doctors actually need to see. And it's all aimed at one single goal: getting the right info to make the right call.
Exactly. It all boils down to a science of trade-offs. You just can't crank up the sharpness to the max without messing something else up. And getting that balance just right, well, that's the difference between a picture that's totally useless and a scan that literally saves a life.
So, what are these critical factors? Well, we can think of them as the 6 pillars of image quality. And once you get these, you'll have a much better handle on how all of this medical imaging really works.
Okay, so here's the list. You've got contrast, resolution, noise, artifacts, distortion, and accuracy. Every single one is a crucial piece of this puzzle. Let's kick things off with the two you're probably most familiar with: contrast and resolution. Yeah, these two are the absolute building blocks. They basically determine what we can see in the first place and just how clearly we can see it. Contrast is pretty intuitive. Just think about adjusting the contrast on your TV, right? It's all about making things pop, making them stand out from the background. In a medical scan, high contrast is what makes it possible to easily tell the difference between, say, a tumor and the healthy tissue around it. It's all about visibility. Okay, so if contrast makes things stand out, resolution is what makes them sharp. It's the difference between seeing one big blurry blob or seeing two separate, distinct points. High resolution is what lets us zoom in and see all those tiny, intricate details of our anatomy. So, you might be asking, how do engineers actually measure this stuff? How do they balance contrast and detail? Well, they use a tool called the Modulation Transfer Function, or MTF for short. The easiest way to think about it is like a report card. It literally grades the scanner on how well it preserves detail, from the big stuff to the tiny stuff. And this chart just illustrates that trade-off perfectly. Take a look. You've got two systems here. System 1, it's great for seeing big, coarse structures. But check out System 2. It's the champion when it comes to capturing those super fine, tiny details. So, which one's better? Well, that's the trick question. Neither is. The best one depends entirely on what the doctor is trying to find. All right, but making a great image isn't just about what you capture. It's also about all the stuff you don't want to see. And that brings us to let's call them the unwanted guests in pretty much every scan: noise and artifacts. Noise. You've seen this before. It's that random, grainy texture in an image. It's basically statistical static. And if you get too much of it, it can completely mask what the doctor is trying to see. It's like trying to hear a tiny whisper in the middle of a loud, crowded room. Now, artifacts are a whole different beast. They're not random like noise. No, these are structured errors that show up in the image. They can be caused by the imaging process itself, the patient, even the machine. And the scary part is they create false features, things that look real, but just aren't there. And as you can see in this table, different problems create their own unique types of artifacts. So if a patient moves just a little bit, you get these streaks. A metal hip implant, that can create this weird star-like pattern. A detector that's out of whack can cause rings to appear. Radiologists and techs actually have to learn to recognize these patterns so they don't mistake them for something real. Okay, so here's a really crucial point. You could have an image that's super sharp, with no noise and no artifacts, but if it's not truthful, it's useless. And this brings us to our final two pillars: distortion and accuracy. Distortion is pretty much what it sounds like. It's when the image doesn't faithfully show the real shape or size of things in the body. It's like a funhouse mirror. It might make something look way bigger or smaller or a totally different shape than it actually is. And you can imagine that could lead to some really serious mistakes. For example, just based on how far an organ is from the X-ray source, its size in the image can get magnified. And because the imaging beam itself often spreads out, an object's shape can get, well, warped. Technicians have to account for both of these kinds of distortion to get any kind of accurate measurement. And this brings us to the final, and you could argue the most important pillar of all: accuracy.
Because at the end of the day, all those other factors, they all serve this one goal. Does the image, with all its good points and its flaws, tell the truth? Does it lead the doctor to the correct diagnosis? That's the only test that really matters.
So how do we measure that? Well, it comes down to two key things. For a test to be truly accurate, it needs to be sensitive, which means it's really good at finding the disease when it's actually there. And it also needs to be specific, meaning it's good at correctly saying, hey, you're healthy, without raising a bunch of false alarms. Okay, so we've met all 6 pillars. Now let's put it all together and see how they interact in the real world. Because this is where the real balancing act begins. And this is the challenge they face every single day. Let's say your goal is to crank up the resolution to see more fine detail. Okay, great. But the consequence might be that you get more noise in your image. Or you might have to use a higher radiation dose, which, comes with its own safety issues. So the goal is never, ever perfection in just one of these areas. It's always about finding that optimal trade-off for the specific question the doctor is trying to answer. So what's the big picture here? What's the main takeaway from all of this complex science? It's this: a good medical image isn't always the sharpest or the cleanest one. A kind of blurry image that tells the truth is 1,000,000 times more valuable than a razor-sharp one that's misleading. So the next time you happen to see a medical scan, hopefully you'll have a new appreciation for the fact that producing that one image was a truly remarkable feat of scientific balancing.
And it really leaves you wondering, doesn't it? As our technology gets better and better and our ability to perfect this delicate balance improves, what new details about ourselves and about our health are we going to discover next?